Hello, and I'm going to be trying to solve question 6.15. It talks about a coaxial capacitor of length equals 6 centimeters that uses an insulating dielectric material that epsilon R is equal to 9. And the right eye of the cylindrical conductor is 0.5 centimeters and 1 centimeter. And they give us the voltage applied across the capacitor, which is this, and it asks us to find the displacement current through this coaxial capacitor. So the first approach you want to take is to write down the equation for the displacement current, which is what they're asking. So I displacement is d over dt, integral d dot ds. Here it's useful to talk about the Gauss's law, because this part of the equation probably looks familiar to you, which Gauss's law is integral s d dot S is equal to Q enclosed over epsilon. So here you're talking about the S's, the ds. And this talks about the surface area. Surface area is a cylinder. So it would be 2 pi RL would be the surface area. If we rewrite this, we can rewrite this as 2 pi RL times E is equal to 2 cubed enclosed over epsilon, which is also equal to Q enclosed over epsilon naught epsilon R, which is equal to E here. Yep, and we have that established. We need to find E in this equation. We need to find E because we're essentially trying to solve this equation where d dot ds, d is equal to epsilon E. So we need to find E in order to find the I displacement. E is equal to E from this equation is equal to Q enclosed over epsilon naught epsilon R times 2 pi R L, the R direction. So I just reorganized this equation. Now we have to find the voltage, because we know that V is equal to negative 0.2 to 0.1 to 0.2 E dot dl. So this is equal to, in this specific question, V would be equal to, we're looking at it from point A to point B, negative point A to point B. E is equal to E from this equation, so Q enclosed, actually I just spaced that in, Q enclosed E naught E R 2 pi RL to the R direction. RL dot dr. And if you look at it, there's an R here. There's an R here, so that's the only thing that actually only be integrated. So this, if you rearrange that, would equal V is equal to, all the rest just comes out, Q enclosed. E naught E R 2 pi L dot ln E over A. B to the value of B. So here, the reason why we needed the V is because we needed to quantify E in a way where we would have information on it using two different equations. So here, if you look at these two equations, the one I highlighted in blue, you find out that the terms on, let me highlight this. You have Q enclosed here, Q enclosed here. E naught ER here, E naught EI here. You have the 2 pi, the L here, 2 pi and the L here. The only thing different is the R's and the L and B. If you rearrange this, the relationships between relationship we'll have E and V. This is going to equal E is equal to negative V over R L N E over A to R direction. And here, now we start plugging in values. V is given in the question. V is given to be 50 sine 120 pi t. Here, E is equal to negative 50 sine 120 pi t over RLN. B over A is also given here. They say the radii of the cylindrical conductors are 0.5 centimeters and 1 centimeter outside. So they're going to try to integrate from B over A, so 1 on the outside, 0.5 on the inside. And the R direction. If you that up, it'll be 2.1 over R sine 120 pi t per meter. Here, we have finally found the equation in terms of the E, and if you recall, we said that the I displacement that we're trying to find, displacement current, is equal to this equation. Let's bring it back down, where D is equal to epsilon E. So let's rewrite this equation. It's D epsilon E equal to EOER E. Here, thus D is equal to E naught is given, E naught is a known quantity, E naught is given to be 8.85 times 10 to the minus 12, I believe. ER is given to be 9 in the question. And E, we just found, is equal to, equal to 9, alright. It's just this equation, this term. 72.1 over R sine 120 pi t. And we're going to try to integrate this over the S, which is the surface area again. It still stays the same, still the cylindrical surface area, which is 2 pi RL. But this time, I'll just write it down, 2 pi RL to the negative R hat direction. It's negative R hat direction because current is flowing from for the terms of displacement current, it's always flowing from the outer conductor to the inner collector. Because R is defined this question to be outwards, for displacement current flowing inwards, it'd be the negative R hat direction. Going back. Thus, now we have to try to solve this. I disp is equal to d over dt d dot 2 pi RL. And that's what this out the integral. And we plug in the value of d. I know it's a lot. So I disp is equal to d over dt 5.74 times 10 to the negative 9. Negative R hat direction, R sine 120 pi t times 2 pi R L. And if you simplify this is going to equal 0.82 cosine 120 pi t and the microamps. And this is how to find the displacement current when you're only given the epsilon values and the length and the radii of the cylindrical conductors. We're using the voltage. So first, to summarize it, first you want to start with thinking about the I displacement values and seeing which variables you would actually need. So we found out that using I displacement values, you need the value of D, and D is found by epsilon E. Epsilon is given in the question. So then you want to go ahead to the Gauss's law to find that D dot ds is also equal to Q enclosed over epsilon, where epsilon is a known quantity, to have more equations, because right now we have two unknowns and one equation. So to find the E, we found out that it's by this quantity, where Q enclosed is still unknown. So you want to find the V value, where you can find the E and the V. After that, you equate those two, find the relationship between the electric field and the voltage value, which from there you found out that the field is equal to a known quantity, and you plug that back into I displacement to find the displacement current. And yeah.